Okay, I'll go ahead and restart real quick. Hi, my name is Will Gross. I am a UTCS undergrad, and this is the first informational quantum workshop for the hackathon happening this Friday through this Sunday. And for this workshop, I'm going to be giving two presentations that cover quantum entanglement, quantum superposition. And then we're going to be watching a 35-minute video from our contact Brian at IBM. And that's going to be kind of an introduction to Qiskit. Now, for this presentation, we're going to be starting at the very beginning of quantum, just in case anyone has no experience with this stuff. We want to give the full exposure. And on Thursday of this week, we'll be kind of giving a more in-depth explanation of Qiskit, projects to make, some algorithms and whatnot. But this workshop is going to be kind of the introductory stuff, along with an introduction to Qiskit. So thank you all for being here, and let's go ahead and get started. Oh, and FYI, since I'm going to be screen sharing, it's going to be a little bit hard to see the chat. So if you have any questions, feel free to put them in the chat. And then at the end of every presentation, I will answer questions. For the code editor to install Qiskit, Brian in his 35-minute video on introduction to Qiskit will cover that. And he'll give you a link and a reference to the IBM website where it'll help you pick whatever code editor you need based on your operating system and whatever device you're working on. So let's go ahead and get started. Screen share. All right, cool. I assume everyone can see me. So awesome. So right now one second, need to present. One second, I'm going to go ahead and close out of Discord real quick. So superposition, which is one of the most basic quantum concepts that allows quantum computing to be possible. So let's go ahead and get into the definitions of it. Excuse me, I have an alarm on my phone. So the basic definitions are two or more quantum states that can be added together or superimposed. And as a result, will be another valid quantum state. And conversely, that every quantum state can be represented as a sum of two or more other distinct states. So essentially, it's when you have two quantum particles or quantum objects. They each represent a separate state, and conventional thinking makes us believe that these cannot act as one state. But in the quantum world, these two objects or particles can in fact be combined and can be measured as a single quantum state. Below that first definition is a lot more of a general and kind of educational definition of quantum superposition. And I have links to these presentations on our GitHub, which I will explain at the end. And if you guys are confused about any of these definitions or would like to review them, that's all available on the GitHub. So for now, I'm going to give a quick Tedx video on Schrodinger's cat to help explain superposition very quickly.
Austrian physicist Erwin Schrodinger is one of the founders of quantum mechanics, but he's most famous for something he never actually did, a thought experiment involving a cat. He imagined taking a cat and placing it in a sealed box with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, what is the state of the cat? Common sense suggests that the cat is either alive or dead, but Schrodinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrodinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory he had helped make and turned to writing about biology. As absurd as it may seem, though, Schrodinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in two states at once, the computer you're using to watch this couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases, and a cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons, one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior, a set of stripes, regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time. A single electron isn't choosing to go left or right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out wave-like orbit. Bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. An electron in a molecule isn't on just atom A or atom B, but A plus B. As you add more atoms, the electrons spread out more, shared between vast numbers of atoms at the same time. The electrons in a solid aren't bound to a particular atom, but shared among all of them, extending over a large range of space. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor or an insulator or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials like silicon. Combining different semiconductors in the right way allows us to make transistors on a tiny scale, millions on a single computer chip. Those chips and their spread out electrons power the computer you're using to watch this video. An old joke says that the internet exists to allow the sharing of cat videos. At a very deep level, though, the internet owes its existence to an Austrian physicist and his imaginary cat.
So yeah, that video is just kind of explaining wave particle duality and just this concept of superposition. We have a tendency to measure things as particles because that's how humans observe things, but in the reality is electrons and other quantum states possess this wave particle duality where they can both be a particle and a wave and thus exhibit properties of both. So this is really important for quantum computing because this principle of superposition allows quantum states to act as wave functions. And because of that, quantum states can be added together as superposition. So as you can see in the right-hand corner, you kind of get an idea of superposition. Perhaps if you've taken a physics class, you kind of know that if two waves are on top of each other, the amplitude is magnified because they stack rather than in particles, which behaves completely differently. But so this unique phenomenon of superposition allows us to entangle qubits together, which is a quantum bit, so that they can act in superposition of each other. And this allows us to do cool quantum things. So your normal computer, the one that you're watching the Zoom class on, has bits that are a 1 and a 0. But a qubit, notated right next to it, and this is Bra and Ket notation, which we'll get into a little bit later. It's the basis of building quantum circuits and establishing a qubit via math. Basically allows a bit 1 and a bit 0 to be simultaneous, acting at the exact same time. In the video that Brian made, we will be showing an example of this, and he gives a good metaphor for it. So we'll get onto that a little bit later. And applications to quantum computing is that rather than bits being discrete binary positions, bits can be represented as wave functions. And rather than having discrete math, like which is the building block of a lot of computational theory and whatnot, we then turn to linear algebra. And the way the math works is that when you have essentially two qubits can be tensored together in order to form essentially a 4-bit state. So the way the math works for a quantum computer is that the math is exponential. Every qubit that you add, you take it to the power of 2, and that's how much computational power that you have. So in a normal computer, when you have 2 bits, you have a 1 or a 0 or a 0 or a 1 for either side. So that means you have a computational power of 2, hence 2 bits. With a quantum computer, when you tensor them together, it actually allows you to create 4 states. And this is represented by this tensor notation together, as you can see. So the 1 can be represented as a 0 or a 1, and then the 0 is a 0 or a 1. And thus you can represent 4 states. If you have 3 qubits, it's 8 states, 4 qubits, it's 16 states. And by the time you get to 50 or 100 qubits, you have, I think 100 qubits is actually more computational power than the biggest supercomputer on the planet. And then 50 qubits, I think, is roughly the same computational power as a brand new laptop. My math could be wrong on that, but what you need to understand is that the qubit math is scalar. Or exponential, my bad. So what's really important for qubits is understanding the probability density function. These qubits, because they are in a state of 0 and 1 at the same time, they are measured via a probability density function. And what this means is that there's a certain probability that the qubit, when measured, and that's how you collapse qubits to normal bits. And there's a certain probability that it will be a 0 or a 1. And when you just tensor 2 bits together normally, it's a 50-50 shot. You have a 50-50 chance of it collapsing to be a 0 or a 1. And when you, when you edit quantum circuits and whatnot, you can actually adjust this probability density function to do cool computation. And by understanding that these qubits are represented by a probability density function, you can do unique problems such as Shor's algorithm to take advantage of the density function so that multiple qubits tensored together have a probability density function that could be altered so that they collapse quicker. I know that may have been a botched example or a botched explanation, but I think the more that you learn, the more that this will make sense. And it is important to know that qubits that are in superposition are essentially probability density functions. So I think we will go ahead and skip this video for now because I think Brian covers it. But for now, we will move on to the next presentation. But real quick, I will check any questions that anyone has. Okay, so it looks like no questions so far. So I think we will move on to the next video if that's cool. I cannot minimize Zoom. Cool. All right, so we'll now move on to quantum entanglement. So we talked about superposition before, and when 2 quantum states are put together, these particles become entangled. So superposition and entanglement kind of go directly together. And the fancy definition of entanglement is that it's a physical phenomenon that occurs when a pair or group of particles is generated, interact, or share spatial proximity in a way that the quantum state of each particle of the pair or group cannot be described independently of the state of the others, including when the particles are separated by a large distance. So that's the fancy scientific definition. The kind of more broken down definition is that 2 particles, can become connected such that when you do something to one particle, the other particle does the opposite, or not necessarily does the opposite, but is at least affected. And this has been shown no matter the distance. You could take 2 particles, separate them, well, you entangle them first, separate them to opposite sides of the universe, and when you affect one, the other will be affected. It's a very cool phenomenon. And this YouTube video, I think, will help explain it a lot better.
Consider throwing a ball straight into the air. Can you predict the motion of the ball after it leaves your hand? Sure, that's easy. The ball will move upward until it gets to some highest point. Then it'll come back down and land in your hand again. Of course, that's what happens, and you know this because you have witnessed events like this countless times. You've been observing the physics of everyday phenomena your entire life. But suppose we explore a question about the physics of atoms, like what does the motion of an electron around the nucleus of a hydrogen atom look like? Could we answer that question based on our experience with everyday physics? Definitely not. Why? Because the physics that governs the behavior of systems at such small scales is much different than the physics of the macroscopic objects you see around you all the time. The everyday world you know and love behaves according to the laws of classical mechanics, but systems on the scale of atoms behave according to the laws of quantum mechanics. This quantum world turns out to be a very strange place. An illustration of quantum strangeness is given by a famous thought experiment, Schrodinger's cat. A physicist, who doesn't particularly like cats, puts a cat in a box, along with a bomb that has a 50% chance of blowing up after the lid is closed. Until we reopen the lid, there is no way of knowing whether the bomb exploded or not, and thus no way of knowing if the cat is alive or dead. In quantum physics, we could say that before our observation, the cat was in a superposition state. It was neither alive nor dead, but rather in a mixture of both possibilities, with a 50% chance for each. The same sort of thing happens to physical systems at quantum scales, like an electron orbiting in a hydrogen atom. The electron isn't really orbiting at all. It's sort of everywhere in space all at once, with more of a probability of being at some places than others. And it's only after we measure its position that we can pinpoint where it is at that moment. A lot like how we didn't know whether the cat was alive or dead until we opened the box. This brings us to the strange and beautiful phenomenon of quantum entanglement. Suppose that instead of one cat in a box, we have two cats in two different boxes. If we repeat the Schrodinger's cat experiment with this pair of cats, the outcome of the experiment can be one of four possibilities. Either both cats will be alive, or both will be dead, or one will be alive and the other dead, or vice versa. The system of both cats is again in a superposition state, with each outcome having a 25% chance rather than 50%. But here's the cool thing. Quantum mechanics tells us it's possible to erase the both cats alive and both cats dead outcomes from the superposition state. In other words, there can be a two-cat system such that the outcome will always be one cat alive and the other cat dead. The technical term for this is that the states of the cats are entangled. But there's something truly mind-blowing about quantum entanglement. If you prepare the system of two cats in boxes in this entangled state, then move the boxes to opposite ends of the universe, the outcome of the experiment will still always be the same. One cat will always come out alive, and the other cat will always end up dead, even though which particular cat lives or dies is completely undetermined before we measure the outcome. How is this possible? How is it that the states of cats on opposite sides of the universe can be entangled in this way? They're too far away to communicate with each other in time. So how do the two bombs always conspire such that one blows up and the other doesn't? You might be thinking, this is just some theoretical mumbo-jumbo. This sort of thing can't happen in the real world. But it turns out that quantum entanglement has been confirmed in real-world lab experiments. Two subatomic particles entangled in a superposition state, where if one spins one way, then the other must spin the other way, will do just that, even when there's no way for information to pass from one particle to the other, indicating which way to spin to obey the rules of entanglement. It's not surprising, then, that entanglement is at the core of quantum information science, a growing field studying how to use the laws of the strange quantum world in our macroscopic world, like in quantum cryptography, so spies can send secure messages to each other, or quantum computing for cracking secret codes. Everyday physics may start to look a bit more like the strange quantum world. Quantum teleportation may even progress so far that one day your cat will escape to a safer galaxy where there are no physicists and no boxes.
So hopefully that kind of helped explain the phenomenon that is entanglement. You have, two particles. In this case, it's the Schrodinger's cat experiment, and the two have become entangled states such that when you measure one, the other is the polar opposite, which is a specific experiment, but has been shown. And that kind of idea of entanglement and entangling qubits is a big building block behind quantum computing. Nope, don't want to play that again. So the implications of this are that when the state of one particle collapses, the other collapses as well. That is true of entangled particles. Particles are in a state of superposition before collapsing, and then when collapsed, the particles are usually polar opposites of each other. That's not always the case of quantum computing. I think I just wrote this in reference to the previous video where they had an example where the two states were perfectly entangled. This can be done with a pair group of particles. You can have a ton of particles that are entangled together such that when one collapses, the entire state collapses. And this helps us with computer and information sciences. And here is another video that helps explain quantum computing with entanglement.
To really understand what is special about quantum bits and why they can provide such a large computational power, we need to look at what happens when we take more than one qubit. Let's take the example of a spin, which we know how to visualize. The superposition of the 0 and 1 state of a single spin is simply the spin pointing to the right. So that doesn't seem so strange. But now let's take two spins and make them interact with each other. This can happen, for example, because each spin produces a tiny magnetic field in its vicinity, and this field changes the energy of the other spin. Remember that we can rotate a spin by applying an oscillating magnetic field at the frequency proportional to the energy difference between the 1 and the 0 state. But if there is another spin in the vicinity, the total energy depends also on the state of that spin. Let's say I prepare both spins in the 0 state, and then I put spin A in the superposition of 0 and 1. Now I try to flip spin B by applying the frequency it would respond to if spin A is in the 0 state. But actually, since A is in both the 0 and the 1 state, then spin B both flips and doesn't flip. The resulting state is a superposition of 0, 1 and 1, 0. The 0, 1 branch of the superposition is created because spin B flips to 1 when spin A is 0. And the 1, 0 branch is created because spin B remains 0 when A is in the state 1. This kind of superposition is perfectly legitimate, but it's really special. In this state, I have absolutely no idea of where the two spins are pointing, but I do know that they point in opposite directions. This is called an entangled state. If I separate the two spins after I have prepared the entangled state, and I measure, for example, spin A, and I find it in the 0 state, then instantly spin B acquires the 1 state, no matter how far apart it is when the measurement takes place. This is what Einstein called dismissively the spooky action at a distance. But now we know from many experimental tests that this is the way quantum mechanics really works.
Yes, that kind of explained more in mathematical terms. Nope, don't want to play that again. In mathematical terms, how that works. If you saw, he was using Dirac notation, which we haven't covered yet, so don't worry about understanding the math of that. Maybe just try to understand that with magnetic spins of particles, he was able to create an entangled state, and that it exhibited the properties of entanglement that were kind of shown in the last video. So quantum computer. So through entanglement, qubits can be intertwined so that with one measurement, the entire state can be collapsed. This effective value sharing via entanglement is used in Shor's algorithm, phase estimation, and in quantum counting, which are three ways of utilizing quantum computers to do certain things. Shor's algorithm breaks encryption. It's one of the most infamous, or specifically RSA encryption. It's one of the most famous quantum algorithms. And it is the most, I don't want to say basic, but it has the most soon application. That was a bad way of saying it, but Shor's algorithm has been demonstrated on a small quantum computer, and if a big enough quantum computer gets built, Shor's algorithm, odds are, will be one of the first algorithms implemented on that computer. And all in all, quantum entanglement is super important for understanding quantum speedup. It's important to understand that by entangling all these qubits together and collapsing the state all at once, you can bypass a lot of computational power, or not bypass it, but just take advantage of quantum states in order to speed up a lot of big problems that classical computers cannot solve. So now that that is over, check and see if we have any questions. Nope, looks like we're all good. Okay.
I have a question.
Yeah, sure.
So like, what if you introduce like a third particle or something? Like, how would the entanglement work?
So the entanglement works is on a, from a physics standpoint, that's kind of hard to explain, but from a mathematical standpoint, each qubit its collapsing can be represented by the probability density function. And so when you have the three qubits entangled together, you have one quantum state. And it is such that every single combination of the three qubits, ones and zeros, so that makes 8 possible states, because you could have all 3 bits being 0, first 2 bits being 0, last one being 1, middle bit being 1, add all those up and you get 8 states. Each one of those has, what's 1 divided by, or what's 100 divided by 8? Something like 16% chance of collapsing to that specific state. Does that kind of answer your question?
Oh, so like it doesn't have the same rule that like one, or like there will be opposite results. So it's not like it's not possible for all 3 to be like in the 0 state or in the 1 state.
No, it is possible for all 3 to be in the 0 and the 1 state. My bad. Sorry for that. Quantum entanglement video, they kind of broke down quantum entanglement to a single example where it's 1 0 or 0 1, where the particles are exactly polar opposites of each other. It is completely possible to have 3 qubits that are all in the 0 state or all in the 1 state or any combination of all of those. It is just a lot easier to explain when you just look at the polar opposites example. Does that by chance answer your question?
Oh, okay. So like for 2 qubits, like it doesn't necessarily always like collapse to 1 and 0 and 0 1 either. Like it is also possible for 0 and 0 and 1 1.
Yep.
Okay.
In that one video, I think he explained that there was a 25% chance for each, but then he narrowed down the experiment by saying we're going to take out the case where both are 0 and both are 1,
Okay.
just so that he could explain entanglement a little bit better.
Okay, thank you.
Yeah, no problem. Cool. Any other questions? Awesome. Moving right along. So next up is the 30-minute video from Brian that covers the hackathon, Qiskit tutorials, and it's kind of the ultimate video on understanding Qiskit and what's going to be happening with the hackathon as well.
Hey there, welcome to the Fall Fest. My name is Brian, and this is the Intro to Quantum Computing workshop. In this workshop, we're going to be going over some of the true basics of what quantum computing even is, how you can start using one today for free, and what you should be thinking about as you move forward in the Fall Fest.
Does anyone object to me putting this at 1.25 speed? Check the chat. Nope. All right, cool. That way we can get a little bit more speed.
In this workshop, we will not be doing any type of the physics or math that are definitely something that you would want to learn as you move forward into your career of quantum computing, or maybe you're just checking it out for now. Either way, this workshop is meant to be accessible to just about anyone. So buckle in, stay with me. It's going to be a lot of fun. All right. So the first thing to know about quantum computing is that sometimes when you screen share, things look weird. Let's do this really quick. Let's do this really quick. And let's just go boom, like that. Now you should be able to see our nice slideshow here. Like I said, this is our Intro to Quantum Computing workshop. I am Brian Ingmanson, who is the Education Engagement Lead at IBM Quantum. I want you to know that anybody can learn quantum. Truly, I mean that. I was a middle school science teacher before coming here to IBM, and I was able to figure out the ins and outs of what's going on here. We've done workshops with actual middle schoolers all the way through grad students and even professionals in the field. So there's something within quantum computing and Qiskit that just about anyone can pick up and start looking at. You know, it might take you a little bit longer to understand really what's going on, but anyone can learn what quantum computing really is. So I want to start by talking about the scale of quantum computing. And I'll start with a question. How many ways can I arrange a dinner party of 10 people? Consider, you know, this dinner party is a staple of my millennial culture. We love our dinner parties, getting everyone's together. And actually this time of year, we're starting to plan our Friendsgivings, maybe. So how many different ways? Think about this. If you know the answer, say it out loud. The answer is 10 factorial, or 10 times 9 times 8 times 7, all the way down to 1. And when you do the math out of what 10 factorial really is, that's over 3.6 million different ways that you could arrange just 10 people at this table for my dinner party. That's a pretty astronomical amount of ways that we can arrange people. And the craziest thing is that every time you add one more person, the problem grows exponentially. So very quickly, what was a simple task turns into something that even some of our strongest computers struggle to look at. Some problems are bigger than you think. So you might be saying, well, yeah, we have really strong computers already. You know, my calculator on my phone can do 10 times 9 times 8 times 7. And you are correct. Yes, we absolutely do have those computers already. In fact, IBM has one. We have the Summit supercomputer. This thing is a beast. It has over 9,000 IBM Power 9 CPUs and 27,000 custom NVIDIA GPUs, all inside of it. And it has 2.5, I believe this is a number too big that I don't even know the right terminology for it, bits of storage. That is a lot of information that this computer can process. But that all being said, it's still not enough to perfectly model something that many of you probably consume every single day, which is caffeine. That's right, caffeine. This is a caffeine molecule right here. There are traditional methods that we can use on computers to approximate a lot about the caffeine molecule. But if you wanted a computer to represent a caffeine molecule at one single instant with complete fidelity, it would take roughly 10 to the 48 bits of storage to look at. So using a classical computer, which is, you know, your laptop, your phone, any type of computer that you have known up to today, it would take, like I said, 10 to the 48 bits of storage. And that Summit supercomputer has less than half of that. And yet, caffeine still exists. Even though our computers can't perfectly model what caffeine looks like at one single instance, where all the electrons are, how they're interacting with each other, what bonds have been created, nature has already found a way to understand what caffeine should look like. So nature knows the answer already, right? Our computers are just trying to catch up with it. This just goes to show that some problems, like a caffeine molecule, are too small for us to see clearly. And this dichotomy of big and small is exactly where quantum computing lives. When we talk about quantum mechanics, we're really describing how things behave on a really small scale, things like atoms and electrons. These very small things just behave differently than what humans are used to seeing in our world. Sometimes it's hard to describe. These really small things are what enable us to study extremely large problems like the one above. Quantum mechanics allow us to approach these large problems in new and unique ways, small and large at the same time. That is where the potential of quantum computers comes in. Scientists think we're only a few years away from a quantum computer that could perfectly model not only caffeine, but hundreds of other molecules for scientists to study. We think we're close to a quantum computer that can analyze extremely large numbers in minutes instead of days. So we are harnessing the laws of nature to tackle hard problems. Quantum mechanics, the laws of nature, the laws of how really small things work, our computers are harnessing that to approach these problems. And so that's essentially saying that quantum computing is creating this new paradigm in how we solve problems. It provides us with new algorithms, new approaches to problems, and new technological breakthroughs that combined have the chance to truly change the world. So all of this can happen thanks to a qubit. Let's talk for a second about what a qubit is and why it is special. The name comes from its description. It's a quantum bit of data. Qubits have special properties, which we're about to look at, and there's actually a few different ways to physically make a qubit. At IBM, we make them one way, but other companies that you may have heard of in quantum computing make them differently. It's similar to a bridge, right? Bridges all have the same purpose, but you can construct bridges in different manners, and each one has varying strengths and weaknesses, same as a qubit. So the first interesting thing about qubits is that we can put them into something called superposition. Superposition, let's imagine you have 3 pennies. When they're sitting on the table, each can only be in one state, heads or tails, right? It's just sitting on the table as either heads or tails. And that means when you look at all 3 pennies, they can only be in one unique order at a given time. I have all 8 possible orders listed here, but the order that we are currently looking at is heads, heads, tails. So when a coin is spinning in the air, its state is that it has a 50% chance of landing on heads and a 50% chance of landing on tails, right? Like, unless the penny is weighted, it's going to be a pretty equal chance that it lands either way. So if I flip 3 pennies at the same time, what order are those pennies in? Think about think about that for 1 sec. Right? What order are those pennies in if they're all spinning in midair? Well, in the world of quantum, aka things the size of atoms and electrons, each penny can be in both states simultaneously, heads and tails. Or a better way to say it, a more scientifically accurate way to say that, is that the pennies are a combination of states, right? A combination of a probability that it might be heads and a combination of a probability that it might be tails. It's equally likely that when the coin stops spinning, they will be in any of those 8 states. In quantum mechanics, we call this superposition. So let's explain the power of what that means, right? In classical computing, to look at 8 different states, I would need to run my program 8 different times. On the first run, we look at head, head, head. On the second run, we look at head, head, tails. Next, head, tails, head, and so on until we got through all 8. In quantum computing, I only need to run my program once to see all 8 states thanks to superposition. It's an exponential speed up of what we can do, right? For n amount of qubits, you get 2 to the power of n different states that you can look at. So superposition allows us to look at some really big problems like chemistry and optimization problems in much more efficient ways thanks to this speed up. Every time you add 1 qubit, the total amount of states doubles. This is the same as that dinner table problem, actually. Every time you add 1 person to the dinner table, the amount of possible states that you could put those people in doubles. Same here. So we're using that to our advantage here. The second thing here is about entanglement. So this one is hard to really describe in a way that makes sense in our normal world, because entanglement isn't really something that we see exhibited in our normal world. We said that quantum mechanics can be weird, right? Well, this is one of those weird things. It's hard to describe what's going on. And even Einstein said that this was something weird. He called it spooky action at a distance. But you could think of entanglement kind of like 2 qubits that become entangled become correlated. So even after those 2 qubits have been separated, when you look at one, you observe one, you learn something about the other, no matter how far away it is. So that's a really key thing here. When you entangle qubits, you're essentially learning about both qubits, even if you only look at one of them. All right, so to recap, quantum computers use special bits of data called qubits, which follow the laws of quantum mechanics. We use those laws to our advantage, enabling us to put qubits into superposition or to create entanglement. And using these techniques, quantum computers harness nature to compute problems that are too large for classical computers to solve. Let's talk about what they actually look like. This right here is the IBM Quantum System 1. Now, this is actually so old that it has our old branding on it, as you can see. We are now IBM Quantum, right? But this was the world's first fully integrated, universal, approximate quantum computing system, designed and built to scale scientific and...
Apologies, having a little bit of an audio issue right now. I'm gonna refresh it real quick.
The dark blue squares, those are the qubits, or our quantum penny.
Oh no. So sorry, guys. For some reason, the audio seems to be doubling.
processing chip. It's about the size of a stamp. So within that big shiny,
Hey, Michelle, are you there?
Yeah, what's up?
Do you mind, so sorry to be doing this. Do you mind actually pulling up the video and sharing it from your computer?
Yeah, let me. Can you send me the link real quick?
Yeah, I am so sorry about this. My computer, for some reason, it does this like once a month, and I hate that it happened now, but sometimes the audio just starts doubling randomly. But yeah, I can send you a link immediately.
No worries. Yeah, just send it in the Discord.
Put it in the chat and in the Discord. That way, also, if anyone wants to copy that link, they can play it for themselves.
Oh, it's not copying. Okay, hang on. Oh, do I have sharing permissions? Wait, Will, can you give me sharing permissions real quick?
Yes, we'll do. All right, there you go. You have sharing permissions. Sorry about that.
Do you remember the timestamp that we were at?
Yes, it was at roughly 13 minutes.
Okay, gotcha. Well, let me know if you guys can't hear this.
In the meantime, get a cup of coffee or some water or something. I cannot hear it right now, unfortunately.
You can't? Okay.
in that big shiny
How about now?
column is our chandelier.
Yes,
And
I can hear it now.
look like a big chandelier full of cables for sending data and maintaining the environment. Way at the very bottom of that chandelier is the quantum processing chip. It's about the size of a stamp. Everything else there is used to help send data and maintain the environment that that chip at the very bottom needs to have. So this is a zoomed in view of that chip. You can see the different parts of the chip itself here, right? Those dark blue squares, those are the qubits, or our quantum pennies. Those squiggly lines you see are microwave resonators, which is how our pennies talk to each other, or how our qubits talk to each other. And that's also how our computers, like the one you're watching this on, send instructions to those qubits. For all this to work properly, it needs to be colder than outer space, or 0.015 Kelvin. And getting the system that cold allows our qubits to behave in a truly quantum way. So here's our systems on the left and one of our researchers, Nick, on the right. Qubits are very fragile and they don't like to be annoyed by things like air or light. So scientists had to build a container that would keep all of these factors away from the qubits. Those cables that you see are those coaxial cables that send and receive information from the qubits. And we have many layers of shielding that protect the processor from any radiation. We also use an electronics rack, which you can see in the picture on the left as well, that sends signals in and out. Here's a video of all of this happening. So from my laptop, I sign into IBM's quantum computer online, and I send some instructions to the computer. Those instructions come to our computers, our array, that transform that command into microwave pulses. And those microwaves travel down to the qubits themselves, and they talk. They give it instructions, and the qubits respond in some way. They send back their results. Our computers analyze those results and turn that into a binary, which then comes back to you at your computer. And that's the whole process. It happens in seconds. The next thing I want to talk to you about is what these computers can even be used for. Now, as part of these Fall Fest hackathons, you are going to be building a project using Qiskit, which is our open source SDK for actually working with quantum computers. So you need to know a little bit about what to even do here. I'm going to talk broadly at first, and then more specifically at the end. You could think of this as like a near versus far term situation. Cell phones today can do a lot more than just make a phone call, right? You can text your friend, you can take a picture, you can read news from anywhere around the world. You can watch videos of things that you think are interesting. You can watch this video right here. You can invest in the stock market, order a car to pick you up, send someone money, order a pair of Louis Vuitton heels, and you can even try to cop a pair of Jordan 1s on the sneakers app, as long as it doesn't crash every Saturday morning like it does for me. But if you think of quantum computing as a timeline, we are much closer to the phone on the left than we are to the iPhone on the right. In quantum, we use the term near term and far term to talk about these two timelines. Near term results on a quantum computer are like what we achieved with cell phones in the 1990s, right? Progress, we're getting there. We're showing that these things can do significant work. We're showing we can make them better, faster, more reliable, but we're not quite at the point of what the iPhone did, right? That's what we would consider far term results. So that's stuff that maybe we haven't even thought of yet. In the 1990s, it would be hard to describe to someone that I am able to use my phone to both play Candy Clicker as well as to order stocks, right? By tapping on it. That's just something that didn't really make sense back then. With quantum computers, we're at a similar place where some of the things we hope might happen one day, we're not even sure what that could be yet. You may have also heard of something called Shor's algorithm. So a perfect quantum computer using Shor's algorithm could crack today's encryption in a matter of hours. Encryption uses really, really big numbers to hide your information with. It creates a special key based on that huge number, and it locks your information away behind it. And now, to be clear, a classical computer can find that key and look at all your secrets. It's just that with most of the good encryption we have today, that would take a couple thousand years to actually crack. Quantum computers have the potential to crack this type of encryption in a matter of hours, not millennia. A very smart man named Peter Shor, who's still alive, still with us, he's on our YouTube channel, he looked at the potential of quantum computers and came up with an algorithm focused on factoring those gigantic numbers, which is how you find that secret key. Using a quantum computer, you could break the encryption on secret documents, conversations between world leaders, bank information of CEOs, and even see the Snapchat that your crush just sent to her best friend about you. That's truly scary stuff. But reports of encryption's death are greatly exaggerated. This is a far-term application of quantum computers. We think it's probably decades away, and by then, our encryption technology will have moved much further forward and be quantum-proof, you might say. Chemistry is something that can be described as both near-term and far-term. So scientists have already used quantum computers for real-world results in the field of chemistry. And actually, IBM, we were super excited that some of our research made it to the cover of Nature magazine here as well. It's not just that we're making the cover of Nature with our stuff either. It's that we are actually improving on this research as we move forward. So here's one of the experiments that we got on the cover, right? It's for using a quantum computer to understand the molecule lithium hydride. We were able to find this exact same result with a 10 times improvement on our research using the exact same hardware year over year because we used better error mitigation techniques. So error mitigation is still something that is definitely a part of the field of quantum computing. You don't really think about errors too often on your phone or on your laptop because we've gotten really good at fixing errors on a classical type of computer. But in the field of quantum, errors are still very much a thing because quantum is still very new. We're working on it all the time. And so we're simultaneously working on our hardware and our software to make the error rates go down and make our results more stable. Gaming is also something that quantum computers can be used for right now, both educational games and games that use quantum computers for generation of those games assets. These are things that already exist. What you just saw on the screen is called Hello Quantum. That's a smartphone app made by one of my colleagues, James Wooten, and it's something that you can go download right now. We also have something called Qiskit blocks, which is like a Minecraft type of game where you can learn the basics of manipulating a qubit through challenge rooms, kind of like Portal, the challenge rooms, right? So these are games that are using the fundamentals of quantum computing within them, something that you could absolutely think to do during your Fall Fest. You can check out Qiskit blocks or Hello Quantum by Googling either of those. Okay, So let's code a quantum circuit. For most of history, to access a quantum computer, you had to build it and maintain it yourself. But 4 years ago, that changed when IBM Quantum, and 5 years ago, now that it's 2021, that changed when IBM Quantum put our systems on the cloud for free for anyone to use. Since then, we've seen enormous results. We have over 160,000 users with over 80 billion executions and 200 scientific papers published about our systems and the results that have been created on those systems. And we're continuing to make our most advanced systems available to users via the cloud. We are going to go on to the IBM Quantum Experience and code our first quantum circuit. So let's do that right now. Okay. When you log into quantum-computing.ibm.com, this is what you would see. This is your homepage. It has news over here on the right. It's got links to the Quantum Composer and the Quantum Lab on the top left, and information about both the jobs that you've sent in and the services that we offer. I'm going to open up the Quantum Composer, which is where we can put together our first quantum circuit. So a circuit on a quantum computer is kind of how we reference the code that's actually running here. Up front, right in the middle here, this big series of lines, this is our timeline. This is our composer, where you can drag and drop different instructions to our qubits. Each line, you can see Q0, Q1, Q2. Each line here represents a qubit. And as we move along the line, that represents our timeline of what we're doing to the qubit at different moments. On the right-hand side, you can see this Python code. This is actually created in real time. So as I drag one of these gates onto my timeline, you can see the Python code over here updates. And hint, this is Qiskit code. This is what Qiskit is. All right, so here's what I'm going to do. I am going to, I'm sorry about that. Let's just delete this guy real quick, boom. Okay, I'm only gonna work with 2 qubits to start. So I'm gonna delete that one. And you can see this C2, that's our classical register. That's where when we measure our qubits, that's where we measure them to. I'm gonna take my first qubit 0, because we always start counting at 0. And I'm going to put this H gate on it, which stands for Hadamard gate. And a Hadamard gate is essentially how we put a qubit into superposition. Now you notice at the bottom of the screen here, our state vectors changed. And I'm actually going to look at our probabilities instead. That might make a little bit more sense for right now. So without anything on our quantum circuit, our probability to measure 0, 0 is 100%. So the probability that we would measure the state 0, 0 after we run the circuit is 100% because we haven't done anything to either of these qubits yet. Qubits start in their ground state as a 0. So if we don't do anything, we're going to measure 0, 0. But like I said, let's take that Hadamard gate, that H gate, and put it on our first qubit. And you can see instantly our probability changes. Now we have 4 possible options down here. We have the options 0, 0, 0, 1, 1, 0, and 1, 1. And so after I've put my first Hadamard gate onto my qubit, it's interesting that we have a 50-50 split between these 2 options. That's because when you put a qubit into that superposition, it now has that equal chance, that 50-50 chance that when you measure it, it will measure as a heads or a tails, measure as a 0 or a 1. So how come it's the right qubit and not the left qubit if this is our first one? Well, that's how we count in quantum computing. We count from the right side over. So as you add more qubits, you can see the very rightmost number, this 0 or this 1, this is the one we're editing on our first qubit. Okay, so after I've put my qubit into the superposition, I want to entangle it. So I'm going to take this gate called a C0 gate, and I'm going to put it on qubit 1 with a target on qubit 0. I'm now entangling these 2 qubits together. And remember, entangling is when we put the qubits into a state that when we measure one, we learn something about the other. And now the probabilities here stayed at 50%, but you can see an interesting thing happen. We moved from it being 0, 0 and 0, 1 to now 0, 0 or 1, 1. So what happened there? Well, when we entangled our qubits here, we've now correlated their result. So when we measure it, if qubit 0 is a 0, so will be qubit 1. If qubit 1 is a 1, so will be qubit 1. Qubit 0, qubit 1. Qubit 0's timeline right here, qubit 1's timeline right here. So that's what our C0 gate is doing. It's making sure that if our first qubit is a 0, the answer for the second qubit is the same. Now you can see there's a lot more gates here. I'm not going to go into detail about any more today, But if you want to learn more about these, we have documentation throughout the IBM Quantum Composer that you can use. We also have tutorials on our GitHub that you can use as well. If I wanted to run my circuit here, let's take 2 measure gates, make it so I'm actually going to measure what's going on. I would click Setup and Run over here in the right. And when I click Setup and Run, I see all my systems. Now, I, as an IBM employee, I have access to some systems that maybe you do not have access to. But don't worry, when you sign up and make your own account, you will get access to real quantum computers for free. You do not need to pay anything. And you can see they're all named after cities. We've got Bogota, Manila, Santiago. We also have simulators, quantum simulators. Now, if you run something on a simulator, you're not actually sending it to a quantum computer. You're running it on your own device. Your own device is simulating what the results would be if you did send it to a quantum computer. So as you're building your projects, it might make sense to try things out on the simulator first, and then when you're ready to actually send it to a system, to pick one to send it to. And I say that because you'll see here, these systems are live. They're being used right now around the world. Manila has 64 different jobs in the queue, or 64 different circuits that people have sent to it that are waiting to be executed before yours would get a chance to run. So after you've chosen where you want to run your quantum circuit, you look over here at your settings. Now, shots is how many times you'll actually run that circuit. So what's that mean? Well, when we're using quantum computers, we're using tools that have, as we said before, a lot of unpredictability in terms of what the results may be, which is what we want, right? We want there to be a superposition that could be heads or tails. But we also have some errors that come through at times. So we want to make sure to run our jobs a lot of times, in this case, 1,024 times, and then look at all those results together to really see what's going on. All right, so I'm not going to run it live because we're recording. Instead, I'm going to go through and show you some of the other results I've run previously. So here's one that I ran on IBM Lima, which is one of our real systems. And I ran that exact same circuit. You can see it right here. This was my original circuit. So the transpiled circuit, this is what our IBM computers did to what I created in order to make it run properly on our systems. We can go more into depth about that later, but you can also look at the Qiskit code for what I ran. Boom, you can see that right here. So when I scroll up, here's my results. So I got 0, 0, 0, 0, 1, 1. I forgot to delete a qubit on this one, which is kind of what we expected. But for some reason, I also got these 0, 0, 1 and 0, 1 zeros that we would not have expected. That's due to those errors that sometimes come through. So you can see we're working with real devices that are live. They have their own flaws, but they also have things that are really interesting. And in fact, those errors, or the noise as we call it, are things that some of our researchers are actively working to harness, to use that noise to create random numbers or to generate terrain in different video games. Again, something really interesting for you to look at. All right, so I've said enough about Qiskit that it's about time I actually show you it. If you go to www.qiskit.org, you will see our homepage for everything you need to do to get started with Qiskit. Now, you'll be able to read our textbook from here. You'll be able to look at other tools and tutorials from here. But most importantly, you can see our quick start menu. This will tell you exactly how to download Qiskit, the stable install on whatever your operating system is. Or you can even just do it all through the cloud if you want to do it through the cloud. Finally, once you've had everything set up on your computer, once you've learned about Qiskit using qiskit.org/learn, at the Fall Fest, you want to make sure to work with the team and build something awesome. Whether it's something big, something small, whether you're fixing a bug or trying something new that no one's ever done before, we are super excited to see whatever it may be. Okay. So thank you very much for joining our Intro to Quantum Computing workshop. I know that was quick. I'm sure I stumbled over a few things, and it's okay if you stumble as you're getting started as well. We have a huge community that's here to help. Please go to ibm.co/join Qiskit Slack to join our Slack community and ask questions there with anything that you might encounter. Also, look for each Fall Fest will have their own organizers, communication method. So there might be a Discord channel or a custom Slack channel just for your Fall Fest. Thank you all very much. I look forward to seeing what you've built. Have a great day. Don't forget to be awesome.
All right, thank you very much, Michelle. Sorry about the technical difficulties, everybody. I think I'll just go ahead and show one last thing, and then we can open it up to questions. Cool. This is our GitHub. And if you click right here, we have quantum educational information. I have all the PDFs on here, as well as 2 more. This is
Can you
one
link
on
to
short.
GitHub?
Yep.
Yeah,
I will look.
did you, I think I posted in announcements for the fall fester. There's a link to the GitHub along with project ideas. Did you by chance happen to see that? Well,
I did not.
Oh yeah, no, just yeah, I just want everybody to be aware that like I'll be making sure to post like all the resources and learning materials that we have in the announcements channels for the Fall Fest. And I think I did make one for the GitHub, and it has a bunch of project ideas. I think Will, I don't think you're in the that's not the right GitHub. Hang on, let me post the right link.
Yep. My bad. I accidentally uploaded it to the wrong GitHub. Anyway, later today, I will take that same folder and re-upload it to the right GitHub. Apologies, that is the like informational helping us plan stuff GitHub. I'll go ahead and close out of that. I found a PDF that is all of Scott Aronson's notes for his class. It is a doozy. It's like 260 pages, but if anyone would like to skim through that, it's got some good stuff in there. Other than that, does anyone have any questions? And then whoever who asked about the IDEs, Michelle put that in the chat that we will handle that on Friday, just in case you didn't see that. Sorry, Michelle.
No, you're good. Thanks so much for doing the workshop, Will. And I just want to tell everybody that I know it seems a lot to learn, but I will say that the Qiskit textbook in those project resources, I think is one of the best places you can start. And it has really in-depth, easy to digest information over how to build circuits, how different algorithms work, what a quantum gate is. And then IBM also has a really great video tutorial series with Qiskit. And I'll also be sure to post a link to those, I think, games that Brian mentioned as well. But I would say your primary resources for learning Qiskit and a little bit more about quantum would be the IBM textbook, as well as the video series, which are both included in that GitHub link. I think that's all I have on my end, but I do want to thank you guys for being here. We're really excited that you're part of our first ever Qiskit hackathon, and we really have a lot of cool guest speakers for you guys planned, and I hope you guys have a fun time. But thank you so much for coming to the workshop today.
Yeah, thank you guys very much for showing up. Hope you guys learned some stuff, and I will be available on Discord. I'll also go ahead and just pop my email, or yeah, I'll put my email in the chat if anyone has any questions that would like to email me personally. But other than that, I think we can call it a day. Cool. All right, I think I'll end it. Thank you guys very much.